This is lesson 7.4, vectors in 3 space. We've covered a lot of information about vectors. We know that they are a quantity with magnitude and direction. We know how to add them. We know how to multiply them by a scalar. We know how to multiply them by each other. But so far we've been working in 2-dimensional space, and I think we're pretty aware that real life happens in 3 dimensions. And just to illustrate that, you can think of yourself in a room. And so typically what I'm saying is we work in 2 dimensions. We have a x-axis and a y-axis, and we have all these different vectors that we can work with, Cartesian vectors in 2 dimensions. They have a horizontal component and a vertical component. But real life happens in 3 dimensions. So you can think of yourself in a room, and if you look at the wall and where the two of the walls meet, you could draw a vertical axis, and you would have another one going this way, and you'd have another one going this way along the bottom of the wall, so that anything that was in the room would be in they would be in the first octant. So when you end up doing this in 3 space, here you have quadrants, 1, 2, 3, 4. Over here you're going to end up with octants. There's going to be 8 separate boxes that you could be talking about depending on the positivity and negativity of the points that you're plotting. Now this becomes the z-axis, this becomes the y-axis, and this coming out at us is the x-axis. Now not all 3-space diagrams look exactly like this. The ones we look at are going to be a little bit different. And quite often, if I start to now erase our room, everything in the room is in this first quadrant. If you were going in the negative z direction, you would be going under the floor. If you went in the negative x direction, you would be going beyond this chalkboard looking thing. And if you were going in the negative y direction, you would be going beyond the wall with the couch on it. And negative axes are often, or the axis in the negative direction is often represented by a dotted line to help us remember where we are. But now you can kind of start to picture that you have 8 separate little boxes, and typically we're going to prioritize the first one, but they're really all, it's just like, plotting a point down here would be like plotting a point along the negative x-axis, positive y-axis, and positive z-axis would put you up in this quadrant, or octant. If you had a negative x value, a positive y value, and a negative z value, you'd be down in this 3-dimensional box. It's kind of hard to visualize 3 dimensions on a flat surface, but that's what we're going to try to do. And then one more thing, I guess, before we go a little deeper, is each of these has a plane. So a plane is a flat surface, but it's the whole surface. So this whole thing would be considered the XY plane, okay? It's the flat surface. It has no depth, no forward toward the camera or back into the paper. It's just flat on the paper, and it has an X dimension and a Y dimension. That's a plane, okay? So this would be your XY plane, flat without going up or down on the Z-axis. But then you also have an XZ plane, which would, be like that, and it wouldn't come this way, and it wouldn't go back that way. It would just be a flat plane. And you also have your YZ axis, which would not go into the positive x's. It would have no depth this way. Okay, so a flat surface that's 2-dimensional space is called a plane. So here you have an XY plane. That's what we're used to working with. But you also now have an XZ plane and a YZ plane, splitting up these octants. The way that our textbook most often draws these octant 3-space planes is done by using the right-hand system. So basically, if you hold your right hand out, and the way that your hand is coming from is the positive y-axis, your thumb points up in the positive z-axis, and then your fingers would be coming out at you toward the positive x-axis. So I'll go ahead and draw that. You can kind of see what that looks like. So again, if you held your hand out, then here's the y-axis, and your your arm is coming from the positive y-axis. Your thumb is pointing up in the positive z direction. So there's our negative done by a dotted line. And then x is coming out at you. And negative. So that helps us get a little bit of a visual on it. And now when we start plotting points, basically all you're going to do, so now of course points are going to be given with 3 coordinates rather than 2 because we're in 3 space. But let's just go ahead and plot the point. Plot the point 2, -3, 7. So in order to do this, we're going to pay attention to what each of these points does. What we have here is an x, a y, and a z. Okay? So we're going to look at each of these points. I'm going to start looking at the x, and what we need to do, didn't label my x-axis, positive x. What we need to do is first move 2 units along the x-axis. 1, 2. Okay? So that's our first point of interest. 2 units along the x-axis. Then what I need to do is we're going to move along the y-axis, and we're going to move along the y-axis in the negative direction 3 units. So I can think about that right here along the y-axis. I can go 1, 2, 3. And if we were just on this xy plane, you can already kind of see, just like if we were over here, and I plotted, 2 along the x and 3 along the y, the point would be where those 2 lines meet, right? Well, I'm going to do the same thing here. I'm going to, because we went -3 in the y direction, I'm actually going to go from my point that is +2 on the x-axis. I'm going to draw a dotted line parallel to my y-axis, and I'm going to go 1, 2, 3. Okay? Now that also means that I could draw a dotted line from here through there, and this line segment should end up being parallel to this line segment, and it should have a length of 2. Okay, my drawings are never going to be absolutely perfect on the little whiteboard here, but that is now, if we were in 2D space, that is the intersection of x equals 2 and y equals -3. Now let's consider what happens when we can take on z equals 7. So we're going to move 7 in the positive z direction. We're going to move 1, 2, 3, 4, 5, 6, 7. Now that's great that I did that there. That's going to give, you can kind of see how now it's not going to form a rectangle like we did over here, but it's going to end up forming a prism of some sort, okay? But what I really want to do is I want to take this, there's a couple different ways you can do it, okay? Because I can take this across and represent my -3 on my y-axis, and I'd start to finish out my prism. But what I really want to do is, because this is now my first intersection of the xy plane, I actually want my +7 to come straight up from there, parallel to the z-axis. So let's do that first. I'm just going to draw a dotted line because it's a bit longer and I want it to be good. I'm going to use my ruler. That looks about parallel. So I'm just going to draw this dotted line, and I'm going to extend it a bit further than I need to. And now I'm going to count up 7 from here. And actually, in order to do that, maybe the best way would be to finish out my prism here. So if I come out -3 here, and I come up 7 from here, and then I can take my -2 in my x direction, -2 in my x direction, then that's where I end up, okay? And this is the point that I'm interested in. Let's call it point P. This is the point 2, -3, 7. And we can double check how we got there. If I'm starting at my origin, okay, then I've got 2 in the positive x direction, -3 in the y direction, so 3 negative y, and then I'm going up 7 in the z direction. And I could finish out this whole prism that is being built. You can kind of see here that it should be going 3 across here, and then 2 here, and then 7 here. Okay? Now there's a whole bunch of points, right? There's 1, 2, 3, 4, 5, 6, 7, 8 vertices here in the prism, but we need to make sure that we're getting the one that we actually want. It's going 2 in the positive x, 3 in the negative y, and then 7 in the positive z. Okay, so it helps to think through or even draw those line segments when you're done. And now what vector could that be? We're not really at this point yet, but what did we just do? Well, we created the vector OP in three-dimensional space. That's what today is all about. We've just done a quick example there, and we're going to do a few more. On the examples printout that I posted on Edsby, I actually gave you a whole bunch of these types of diagrams. I think they look like this because that's what we're doing in our textbook. So that you can follow along on those, or you can quick sketch your own in your notebook, your choice. Or you can cut them out and tape them in, whatever you want to do, okay? Okay, example 1 really exists just to help us visualize these octants again a little bit better. It probably is helpful to think about it as a room where the positive x, positive z, positive y creates this box, creates the octant, where the things in the room are. And then if you were to push beyond the wall that you're looking at, right, then you'd be in the negative x direction. And if you were to push beyond the wall at the side where I had drawn that couch, then you'd be in the negative z direction. If you were to go below the floor, then you'd be in the negative y direction. And even you can see below the floor, there would be 4 boxes. There would be just directly under the room. There would be directly under beyond the chalkboard. There would be directly under beyond the wall where the couch was, and then there would be the far bottom left kitty corner area, another box, okay? And then you have come above the floor, and you have the same thing. You have the room, you have beyond the room to the left, you have beyond the room, beyond the chalkboard, and then you have that kitty corner in the back left. So we're just going to think about where these points are. Probably not even going to draw them, we're just going to think about them. So again, this one has positive x, positive y, positive z. So it's in this top front right box. Okay, this quadrant with the solid black lines, it's in there. Okay, it's a quadrant, octant. So it's a box above 0, to the right of 0, and toward us. If we look at x equals negative 3, 2, and 1, positive, positive, positive y, positive z, then we're in the same, you can think of that, the box that we were in, the front right box, and now all we're going to do is push it back, basically beyond the chalkboard in my original drawing, and that's where it's going to be, okay? Well, now look at this one. We have negative x, negative y, negative z, so this is going to be in that obscure back left bottom corner, okay? If you're looking at it from the room, you're kind of looking down at the corner of where the 2 walls meet, and then you're looking past that point. I'm in a basement, so that's like real deep down into the ground, back away from me. Negative, negative, negative. All right, what about this one? Positive x, positive y, negative z. So we're thinking about our xy plane, but then we're going to push it back into the negative z land, okay? So we're front, right, bottom. All right, hopefully you can think through that if you want to kind of do that again, but we're going to be doing it throughout, so you'll get it better maybe as we draw these things. And that's our next example. All right, example 2, we're going to be plotting some points in 3-dimensional space. I've got them lined up here, A, B, C, and there's D. We're going to have to scroll over when we get there. But again, you can use the diagrams that I've printed for you. I haven't printed them. I posted them on Edsby. Or you can just go ahead and quick sketch your own. They don't take long once you get used to it. And basically what we're going to do is we're going to represent the X, Y, and Z dimensions of this point using line segments. So first we're just going to head positive 2 in the X direction. 1, 2. Okay. Then we're going to head from there. We're going to head 6 in the positive z direction. Okay, 1, 2, 3, 4, 5, 6. And again, mine is a bit sketchy because I don't have any values on my axes, and it makes it a little bit easier. But basically, I should have been able to, if you do, then basically you're starting from 6 along the z, and then you're going to come back forward, I guess, these 2 along the x. So you can start to see that this is now your first point of interest. I'm going to erase that line, so I don't actually want it. This is my second line segment. That's helping me draw the point A. And now I'm going 1 in the y direction. And that looks like this. Straight up 1 in the y direction. Okay? So this is where that point is. Point A, right here. Let's do this in my arrows in a different color, but this is point A at 2, 6, 1. And again, if you want to double check that you've done the right thing, you can kind of finish out this diagram. This would be from here I'd go 1 vertically along the y. From here I'd go 1 vertically along the y. From here I go 1 vertically along the y. Here I'm going to have my positive 2x. Here I'm going to have my positive 6 along the z. Here I'm going to have my positive 2 along the x. And then I've pretty much, yeah, finished out that diagram. And again, just make sure you're not, tracing these lines every which direction in order to get to where you're going. Make sure that you have 2 positive x, 6 positive y, and 1 positive z, and boom, there you are. That's A. Okay. I'm going to draw these diagrams just a little bit smaller. And this one. Okay, not so painful. Y, Z, X. And for point B, we've got 0, 0, negative 6. Well, that one's pretty straightforward. I'm at the origin. I'm not moving anything in the X direction. Not moving anything in the Y direction. I'm just, these are backwards. Yep, I did that backwards. I think I talked about it correctly. Z, Y, Z, Y. Okay, sorry about that. I'm not heading anywhere in the X direction. I'm not heading anywhere in the Y direction. I'm just going negative 6Z. Well, here's Z, 1, 2, 3, 4, 5, 6. Boom. Okay, draw a line segment to help me visualize it. This is now the point B at 0, 0, negative 6. Pretty straightforward. Yeah? All right, scrolling over, make some room for C. Just gonna erase that. Again, you could even just draw them with all solid lines. X, Y, Z, and then come through and just give yourself that dotted. Wrong way. Okay. Clever use of an eraser. Thanks very much. Okay, positive 2 in the X. 1, 2. Line segment. Done. Positive 3 in the Y. 1, 2, 3. 1, 2, 3. Do. There it is. And 0 in the Z direction. So that point is then on the XY plane, okay? Because it's 0 up and down. There is no height to this thing. We ended up just creating a square, a rectangle. It's not a square, it's a rectangle on the XY plane. So this is the point C, 2, 3, 0. And the last one, won't make you watch me draw. Point D, negative 1 along the X, negative 1. Negative 3 along the Y. 1, 2, 3. 1, 2, that's pretty bad. 1, 2, 3. Okay. And so this is this I shouldn't have drawn, that should be dotted, but this is our point of interest so far. And now 4 up in the Z direction. 1, 2, 3, 4. Okay, there's our point. Point D, -1, -3, 4. And if I want to finish off my prism that we've drawn, okay, it's -3 in this direction. It's -2 in the x direction. And it's up 4 in the z direction. Up 4 in the z direction. -2 in the x direction. Sorry, I'm saying that wrong. -1 in the x direction. And -3 in the y direction. And there you have it. Okay, finish it out with this guy, and this guy. Lovely. There's drawing 3D, drawing points, plotting points in 3 dimensions. Well, just like when we were working in 2D space, we could take any vector and represent it as a Cartesian vector by simply moving its tail to the origin. So all I'm going to do here is I'm going to take any vector, okay? There's our vector, vector v. And I'm going to simply take its tail and translate it to the origin of our 3D Cartesian octate, or whatever you want to call that. So we have our vertical axis, which is z. We've got a y dimension, and we've got an x. Well, just like when we were working in 2-dimensional space, we could take any vector and represent it as a Cartesian vector by simply taking its tail and translating its tail to the origin. And we can really do essentially the same thing in 3-dimensional space. So if I take any vector, let's call this vector v, and I'm going to take its tail and translate it to the origin of our 3-dimensional space. So here we have our positive z axis, positive y axis, and then we have our x axis coming out at us. And in order to represent this vector as a Cartesian vector, all I'm saying is that from O to P, some point P with dimensions x, y, and z, coordinates x, y, z. So what does that look like? Well, if we go some amount, that just means that point P can be found by going some amount in the x direction, some amount in the y direction, and some amount in the z direction, okay? So we went this far in the positive x, we went this far in the positive y, and this far in the positive z, and we ended up at point P, which now can be represented by the coordinates x1, y1, z1, which means that our vector v, represented here in blue, is the line segment OP from the origin to point P, and it can be represented with square brackets as x1, y1, z1. And again, if I wanted to finish out this diagram, if I wanted to finish out the prism that I make, then just from each point, up, across, over, across, down, down, and there's our prism, okay? And you can see now that we have these 3 x direction, y direction, z direction to get us to point P, which gives us vector OP in 3-dimensional 3 space. All right. Now, this vector has the same direction and magnitude as OP, which is the point in 3 space. If it's helpful, let's quick jot down what we just did. We said let V be some vector, any vector, in 3 space. Next, translate the tail of V to the origin. translate the tail of v to the origin. Then the tip P is at x1, y1, z1, and v is the position vector of the point P. The vector v equals line segment OP in 3 space, which is the vector x1, y1, z1. Okay, this is generalized language. As we're doing it, we'll know where the point P is and what vector then represents it and where to plot it and how to plot it, etc. Also, just like in 2D space, we could talk about the unit vectors. We can do the same thing in 3 dimensions. So now, instead of having just the unit vectors I and j, we also have the unit vector k. All right, so the unit vector in the positive x direction, 1 unit long, right here, is represented by the letter I. Find a good space to write this. And I is 1 unit in the x direction, 0 in the y direction, and 0 in the z direction. We're going to do that for all of them. J, the vector j, let me give our vectors arrows. J is 0 in the x direction, 1 in the y direction, 0 in the z direction. And the unit vector k is 0 in the x direction, 0 in the y direction, 1 in the z direction. And again, any vector that we are dealing with in 3 space can be represented as the sum of a combination of I, j, and k, or multiples of I, j, and k. They all have magnitude or length of 1. And so we can build any other vector using these 3 one-dimensional component vectors. So let's jot that down. Any 3D vector can be written as the sum of multiples of I, j, and k. Vectors I, j, and k. So if we take any vector, and if I just go ahead and draw any vector in here in this space, we'll call it vector u, and it's going to look like, I'm just going to erase my negative axes for a second, and we're going to draw vector u out here, let's say like this. Then vector u is represented by the point A, B, C, which makes this the point A, B, C in rounded brackets. And if I'm going to build that by finding my magnitude in the x direction, my magnitude in the y direction, my magnitude in the z direction, then what I'm actually going to have as a magnitude in the x direction is some multiple of vector I, of unit vector I, and the multiple of it is a. So this is, the length of this line is a, I. The length of it is a, and it's in the direction of the unit vector I. Okay? Now we've gone also some magnitude, some distance in the positive y direction. Well, how far have we gone? We've gone b. So b in the direction of unit vector j. So this line segment right here is some multiple of the unit vector j in the y direction. Okay? And same thing here. We've got some multiple c times the unit vector k. And so any vector in 3 space can be written as the sum, the addition, of multiples of unit vectors I, j, and k. And again, to help us visualize it, I could finish out our diagram. Okay, you don't need to do this every time if you're getting good at it. But yeah, that's not straight up. There it is, there it is, there it is, and there it is. Yeah, that looks about right. Good. Continuing our notes, using mostly this diagram to think about, but we're also being able to reference both of them here. We're going to add vectors in 3D the same way as we added vectors in 2D, just like we're doing. We're going to place them tail of the second vector to the tip of the first vector, and then the tail of the third vector to the tip of the second vector, and you basically just add AI plus BJ plus CK, okay? And that will give you vector U. So what does that look like? Vector U here is the line segment from O to P, okay? And you can name this point whatever you want. Sometimes it'll be named S, but P is the most common. So it's the vector OP, and it's built by simply adding OQ to QR to RS, or in this case, I wrote P. But our other diagram, if we're following it around this way, we'll just say the head of the red arrow here is called S, and it happens to be at the same point as point P, because that's where RS ends. At any rate, OP then is OQ, from the origin to Q, plus QR, plus RS. Now a lot of this is, you're kind of intuitively understanding it already. I'm just breaking it up so you can see, well, what is OQ? OQ is some multiple of the unit vector I. It's AI. Well, it's QR. It's some multiple of the unit vector J. It's BJ. And RS is some multiple of the unit vector K, CK. And so, well, what is AI? AI, we talked about over here, is some multiple of 1, 0, 0. Well, what is it? It's A, 0, 0. BJ is 0, B, 0. 0, B, 0. And CK is 0, 0, C. When we put all that together, okay, we really just get A, B, C. All right? Right here, right here. It's a little breakdown of different ways that you can talk about U and how you can get there, how you're adding, how it's helpful to break it into its components along each axis. Okay, well, how do we then calculate the magnitude of these vectors? How do we calculate the magnitude of U, which is essentially the length of OP? How do we get that? And you can kind of see in two-dimensional space that you use Pythagorean theorem, and you end up a squared plus b squared equals c squared. You get the length of the hypotenuse in the right angle triangle that is created. Well, this is going to be exactly the same, except if I take a different color here, you can see you're going to be working in 2 dimensions twice. So if I look at OQ and QR, okay, they actually form a right angle triangle with a right angle right here, because they're on the plane, they're on the XY plane. So just this little box right here is flat on the surface of the XY plane, and the hypotenuse is right there. Okay, so we have a leg here and a leg here. A squared plus b squared equals c squared. And now that we have that, we actually have another right angle triangle. This right here forms a right angle triangle, where you now have the length of one leg, the length of the other leg, and you use Pythagorean theorem to get the length of the hypotenuse of that triangle. So the diagrams can be a little bit tricky because you might say, well, that doesn't look like a right angle. Well, you're on a plane and you've just gone one direction and another direction, and the axes always meet at a right angle, okay? So you are creating a right angle triangle. You could, if you needed to, you could kind of flip that up and say, oh, if I just had an x and a y, and I had my point, you know, over here in the positive positive, well, I could make a right angle triangle. That's exactly what we've done, okay? Where this right angle is on the x-axis, that's what we have. It's on the x-axis. Our hypotenuse right here is right here. And then we're flipping it essentially and saying, okay, let's look at a different plane now, another two-dimensional space. And look, we do have another right triangle on that two-dimensional space. If I draw a line across the xy plane, and then I all of a sudden go straight up off the xy plane, that's going to create a right angle, just like a building coming off of the ground, okay? And so you do have another right angle, you do have a leg and a hypotenuse, and that's the way to do it. Now, there is a way to combine it into one calculation, which you might have figured out already. We said that OR squared, right, according to Pythagorean theorem, OR squared is OQ squared plus QR squared. And then we're going to use OR squared in our calculation of OP squared. It's OR squared plus RS squared is OP squared. And OP is the vector u. So let's look at that for a second. We've got OP squared. That's what we're going for. And we know that OP squared is OR squared plus RP squared. But we already discussed that OR squared is actually OQ squared plus QR squared. So here, this OR squared is actually the same as OQ squared plus QR squared plus, and then we have RP squared out here. Now, we also know that this vector OQ only has an x direction. So it's actually the coordinate, it's the x coordinate of our vector u, a, b, c. It is letter A. QR is the y direction right here. It is letter B. And RP is our z direction. It is letter C in the vector u. So all we really have here actually is the vector u, the magnitude of vector u squared is a squared plus b squared plus c squared, which if we want to, let me move this, if we want to square root both sides, then we get the magnitude of vector u is the square root of a squared plus b squared plus c squared. Not so challenging there. Example 3. Example 3. Working with 3D vectors. For each vector below, 1. Sketch it. 2. Write the vector. Write in form AI plus BJ plus CK. And then 1, 2, 3, 1, 2, 3. Find magnitude. Find magnitude. All right. First one, vector u, 3, -1, 2. We've done some sketching already. I'll sketch this one, but I'm going to stop sketching them. X, Y, Z. negative, negative, negative. All right, first step is sketching it. We have 3 in the positive x direction, negative 1 in the y direction. That's going to go this way, parallel to the y direction, negative 1, and 2 in the z direction. Okay? It's looking like maybe something like that. There's not much. Anyway, here's our vector. Again, your diagrams need to be understandable. So draw this line segment, and this line segment, but are they all going to be exactly perfect looking? Not really. And if you're still confused, you can finish out your parallelogram. And if it works, that's great. All right, there's our sketch. Step 2. So that's 1. Step 2, write it in the form some multiple of I, some multiple of j, some multiple of k. All I need to do is take the values that we have here as x, y, and z and say this is 3 times the unit vector I minus 1 times the unit vector j plus 2 times the unit vector k. And lastly, find its magnitude. The magnitude of vector u, right? Magnitude of vector u is the square root of a squared plus b squared plus c squared, which is the square root of 3 squared plus negative 1 squared plus 2 squared, which is 9 plus 1 plus 4, which is 14. And there you have the magnitude of vector u. Second part, we have the vector v. It is given by negative 2, 0, 1. And we're seeing that this has an x direction, negative x, and positive z, but no y. So this is actually on the xz plane. It doesn't have any left or right here on y. I'm not going to draw it. I'm just going to do number 2, which says write it in the form here. So vector v then is equal to negative 2 times the unit vector I plus 1 times the unit vector k, 0 times j, 0j. Magnitude of v, square root of negative 2 squared plus 1 squared. That's 4 plus 1 is 5, radical 5. Good? Good. We're going to run through some notes that are essentially the same when working with vectors in 2D or in 3D. First one is scalar multiplication. So if you have vector u in 3 dimensions, represented by u1, u2, u3, and any scalar k, which belongs to the set of real numbers, then you can develop vector ku. It's simply going to be ku1, ku2, ku3. And any vectors u and ku are collinear. Okay, if you use the same scalar multiple on each of the coordinates, then you're going to end up with a vector that is either longer or shorter than u, but in the same direction as u, exactly the same direction, all 3 dimensions. So these guys are collinear, okay? That means that if you translated ku, the tail of ku to the tail of u, they would be right on top of each other. They'd lie on the exact same straight line. So how do we find those things? Well, quick example. Example 4 deals with this issue. Collinear vectors. And A says find the letter A so that 1, 2, 3 and 2A, 6 are collinear. Okay, I'm not going to spend too much time on this. You can clearly see that this second vector here, let's call it KU, is a multiple, ought to be, needs to be, in order to be collinear, it needs to be a multiple of vector, let's say u. So 1, how do we get from 1 to 2? Well, you multiplied it by a scalar of 2. So 1 times 2 is 2. Double check. 3 times 2 is 6. Yep. How do I find A? Scalar multiple is 2. So 2 times 2 is 4. Okay, so here A equals 4. Needs to be, because it needs to equal 2 times 2, which is 2 times k. Second one. Second one says find B and C such that negative 2b 7 square and c 6 21 are collinear. Okay, basically I'm looking for a match in order to help myself find k, and k is a ratio. It's going to be 21 over 7, right? Because that's how I'm going to get from each coordinate in my original vector to its collinear vector. Whether I can work backwards too, it's not a big deal. But at any rate, the ratio k is going to be equal to 21 over 7, which is 3. Therefore, C equals negative 2 times 3, which is negative 6. And B, well, B is a little bit different. Here I have B times 3 is 6. Or I could do 6 times 1 over K. Okay, I could take the reciprocal of this ratio, and that would give me B. But I'm just going to write it this way. I have B times 3 equals 6. Divide both sides by 3. B equals 2. All right, C equals 6. It's a funny way to do it. And B equals 2. Now, a bunch of other tools that we still use in 3 dimensions. So we did scalar multiplication, okay? But we can also do vector addition. Vector addition in 3D. And this is just slightly modified. So let's say you have, it's not, I mean, it works the same way. So let's say you have vector u defined by the coordinates u1, u2, u3, and you have vector v by the coordinates v1, v2, v3. Not sure why I put a line there. Then u plus v is just u1 plus v1, comma, u2 plus v2, comma, u3 plus v3. So it's just the sum of each vector, the quantity of the magnitude of each vector in the x direction. Then how far are we going total in the y direction? Then how far are we going total in the z direction? All right, what about vector subtraction? Vector subtraction in 3D. Well, vector subtraction in 3D works the same way. Let's have u and v, then u minus v. The difference between u and v is u1 minus v1, comma, u2 minus v2, comma, u3 minus v3. Carrying on. What about the vector that is not having its tail at the origin? Vector between 2 points. All right, well, let's say we have the vector p1, p2, and it goes from p1, which has the coordinates x1, y1, z1, and it's heading to p2, which has x2, y2, z2. Then p1, p2 is simply the difference in the x's. So it's x2 minus x1, x2 minus x1, comma, y2 minus y1, comma, z2 minus z1. And this is just the change in x, change in y, change in z to get from p1 to p2. And then this new difference vector would be a representation of this vector. It would be the position vector of p1, p2. So just doing this would translate p1, p2 to the, with its tail at the origin. Okay. Last one, magnitude. Magnitude of the vector between 2 points. The magnitude of a vector between 2 points. So you've got point P, point P1 and P2. So we're going to use this same vector basically. We're just finding, well, what's the magnitude of this? Well, if we determined that it's represented by A, B, C, which is the difference in X, the difference in Y, the difference in Z, then the magnitude, pretty simple to understand based on what we've already done, is the difference in your x squared plus the difference along the y-axis squared plus the difference along the z-axis squared, and take the square root of that. You also see how using a strike through your z is really helpful because z's and 2's look pretty much the same, but this is clearly a z because I put a strike through, and this is a 2. Yeah? Saves you some confusion along the way. Okay, so let's do some more work with our Cartesian vectors so we can express them in different ways. We are in A, there's going to be an A, B, C here. It's not going to take a ton of space, maybe half a page. We are given A, which is a point at 3, 6, -1, and B, which is a point at -1, 0, 5. And we're going to express as an, or express what? Express the vector AB as an ordered triple. So in two-dimensional space, we talk about ordered pairs. Here we're going to have an ordered triple. Then in terms of I, J, and K. J, K. So the sum of the multiples of I, J, and K. All right, I'm going to just do it right here. There's not much to it. The vector AB then is the difference in your x's. So there, AB is a vector anywhere in 3 space. And we're going to essentially translate it to its position vector, AB, with its tail at the origin. Okay, so we're just taking the difference, the change in x, the change in y, and the change in z. So that looks like this. So we are going to take x2 minus x1, y2 minus y1, and z2 minus z1. Looks like this. negative 1 minus 3, comma, 0 minus 6, comma, 5 minus negative 1. Close it off. Reduce. Negative 1 minus 3 is negative 4. 0 minus 6 is negative 6. 5 plus 1 is 6. In terms of the unit vectors I, j, and k, you can look over here. This is going to be negative 4i plus negative 6j, so I'm going to go minus 6j plus 6k. B. Magnitude of AB. Well, magnitude of AB. Magnitude. AB. It is the square root of a squared plus b squared plus c squared. 16, 36, 36, 72, 88. Done. And the last section, we're going to determine C. Determine the unit vector U in the direction of AB. Okay, so AB has a magnitude of square root of 88. We're looking for the vector that goes the exact same direction as AB, but has a magnitude of 1, okay? Now, last lesson, we learned that the unit vector in the direction of any given vector is, maybe we'll make a note of this, make a note of it in red, the unit vector in the direction of AB has magnitude, no, the unit vector in the direction of AB is 1 over the magnitude of AB times the vector AB, okay? So this is the vector AB is going to give us the right direction, and then this piece, this factor, is going to reduce or enlarge that vector so that it has a magnitude of 1 unit, okay? So let's look at that. In our case, we're going to let the unit vector be called U, and U equals 1 over AB, the magnitude of AB, times the vector itself. All right, well, we already figured out the magnitude. It is 1, so the magnitude is 80, radical 88, so we've got 1 over radical 88 times the vector itself, which we determined was negative 4, negative 6, 6. And now I'm simply going to, there's two ways that we can do this. You can, first of all, we can simplify this radical, okay, which is going to simplify this equation, which is then when we distribute it, is going to make it a little bit easier to reduce these values. So why don't we do that first? I see I can pull out a square from this. I can pull out 4. So this is radical 4 times radical 22. So I have 1 over, and radical 4 is going to reduce to 2. Because 2 is the square root of 4. And in here we have radical 22 still. Copy down my vector AB. And now I'm going to distribute and reduce at the same time. So my new vector, vector U, which is the unit vector in the same direction as AB, is going to be negative 4 over 2 radical 22 Well, 4 over 2 is 2, so this is going to be negative 2 radical 22. Then I'm going to have negative 6 over 2 radical 22. Well, negative 6 over 2 is negative 3 over radical 22. And my z dimension is going to be 6 over 2. That's 3 over radical 22. Okay, simple application. Here we have the magnitude of the unit vector, which is 1. And here we have the direction, which is in the direction of AB. So our new vector u is some multiple of the vector AB. And last but not least, dot product. 3D Cartesian vectors. For any two 3D Cartesian vectors u with ordered triple u1, u2, u3, and vector v, the ordered triple v1, v2, v3, then the dot product of u and v is u1 times v1 plus u2 v2 plus u3 v3. Okay. Example 6. This is just working through the different operations that we just took notes on. Using Cartesian vectors in 3 dimensions, we're given the vector u with an ordered triple of 2, 3, negative 5, and v, 8, negative 4, 3, and w, negative 6, negative 2, 0. And we are first going to find negative 3v. So negative 3v is a scalar k times vector v. So you've got negative 3. It's going to be collinear to vector v. 3, and then the triple for v is 8, negative 4, 3. We're just going to distribute negative 3 to each of these coordinates. We're going to get negative 24. Negative 3 times negative 4 is 12. Negative 3 times positive 3 is negative 9. B, we've got u plus v plus w. So when we're adding these guys, we can just add them all in series. We're going to end up with, I'll jump down to here, give myself a bit more space. I'm going to add the x coordinates, then the y coordinates, then the z coordinates, and that's going to come out with our new vector. So I've got 2 plus 8 minus 6. I've got 3 minus 4 minus 2, and negative 5 plus 3 plus 0. Reduce. 10 minus 6 is 4. Negative 6 plus 3 is negative 3. Negative 5 plus 3 is negative 2. That is the vector u plus v plus w. C. C asks us to find the magnitude of the difference vector uv. Technical difficulties. Uh-oh. uv. All right. So first we're going to find the difference between those. So it's going to look like this. I'm going to just take the magnitude of, and I'm going to represent vector u as a Cartesian vector, 2, 3, negative 5, and I'm going to subtract vector v, 8, negative 4, 3, magnitude. And from here, we're just going to find the difference between our x's, the difference between our y's, the difference between our z's, okay? And then we're going to be finding the magnitude. So I've got 2 minus 8 I'm gonna skip that middle step here. I'm just gonna do it in my head. 2 minus 8, negative 6. 3 minus negative 4 is 3 plus 4 is 7. Negative 5 minus 3 is negative 8. And now to find the magnitude of that, a squared plus b squared plus c squared, the square root of that. We've got 36 plus 49 plus 64, and that's going to be radical 149. That is the magnitude of the difference vector u minus v. Last one, d. I'm going to squeeze it in over here. U dot v. U dot v. So the dot product of u and v. We're going to write that in our ordered triples. U is 2, 3, negative 5. Dot v, which is 8, negative 4, and 3. And now the dot product, as we just wrote it up above, is the product of the x coordinates plus the product of the y coordinates plus the product of the z coordinates of each of these. So what do we end up with? We end up with, and remember the dot product is not a vector quantity, it's a scalar quantity. So as soon as I do this, I don't have I'm just going to end up with one value at the end, and it's not going to be a vector. Okay, it's going to be the dot product. So here we have 2 times 8. 2 times 8 plus 3 times negative 4 plus negative 5 times 3. 16 minus 12 minus 15 equals negative 11. In example 7, we're putting some things together, some concepts together. The collinear vectors, that is two vectors that land right on top of each other, go in the same direction, they don't have to have the same magnitude. And dot product is essentially multiplying them together. So one of the relationships that we have is that if two vectors are collinear, then what is the angle in between those two vectors? Well, the angle is 0. So we're going to be given vector A, 6, 2, 4, and vector B, which is 9, 3, 6. We can just do a double check right here. If I take 6 and multiply it by 1.5, I get 9. 2 times 1.5 is 3. 4 times 1.5 is 6. So I can see right here that they are collinear. I need to determine whether or not these are collinear. Okay? So to determine whether or not they are collinear, we're going to find the angle in between them using the dot product. So find angle between A and B using dot product. We know that the cosine of theta being the angle in between them, is equal to the dot product of A and B over the product of the magnitudes of A and B. All right, dot product is, well, we'll just plug in our vectors first so we can see what we're talking about. So we've got 6, 2, 4 for A, dot 9, 3, 6 for B, and the magnitudes of the two, again, just plugging in the two, but magnitude. So the magnitude of A is the magnitude of 6, 2, 4, right? Magnitude of B is the magnitude of 9, 3, 6. All right, from here we are calculating the dot product. So dot product is x1, x2 plus y1, y2 plus z1, z2. So 6, ooh, not 2, 6 times 9 plus 2 times 3 plus 4 times 6. And in the denominator, we have the magnitude of these guys. So the magnitude of A is the square root of 6 squared plus 2 squared plus 4 squared. And the magnitude of B is 9 squared plus 3 squared plus 6 squared. Numerator becomes 54 plus 6 plus 24. That is 84. And the denominator becomes 36 plus 4 plus 16, square root of that, times the square root of 81 plus 9 plus 36. And then we can multiply those square roots together by multiplying the value underneath them, the radicand, and we end up with the square root of 7,504. Sorry, 7,056. And if you take the square root of 7,056, you find out that it is 84, which means this reduces to 1. All right, so the cosine of theta then, cosine of theta is 1. Well, where does that happen? That happens when theta is 0. Okay, you can take the inverse cosine of 1, and you get theta is 0. Therefore, A and B are collinear. Example 8, 2 more, 8 and 9. Find an orthogonal vector. Orthogonal vector. Orthogonal just means perpendicular. Perpendicular. Okay? So we're going to prove that two non-zero vectors, prove that A and B are orthogonal if and only if their dot product is 0. Okay, so a little bit of the same concept here. Again, if and only if means if the dot product is 0, then A and B are orthogonal. And if A and B are orthogonal, then the dot product is 0. Okay, so first we're going to prove that they are orthogonal. First we're going to prove that they are orthogonal. That's 1. Then we're going to prove that their dot product is 0. Okay, so step 1. If they are orthogonal, what has to be true about them? Well, the angle between them is 90 degrees. All right, so let's see if that is true. Okay, we have our formula for the dot product. It's the magnitude of A times the magnitude of B times the cosine of the angle in between them. Okay, now if they are orthogonal, the angle between them is 90, so that's there. Well, what is the cosine of 90 degrees? The cosine of 90 degrees is 0. So this whole right side becomes 0. What did we just prove? Okay, we just proved that if they are orthogonal, the dot product is 0. Okay, now we're going to start from the other side, and we're going to show that if A and B, if the dot product is 0, then they are orthogonal. Okay, second part, if A dot B is 0, they are orthogonal. Okay, so it works if and only if means it works both ways. So we're going to let a dot b be 0, which means when we take our formula for dot product, we're going to end up with the magnitude of A times the magnitude of B times the cosine of angle theta, whatever that angle is going to equal 0. The dot product is 0. Since the vector A cannot be 0 and the vector B cannot be 0, then we can divide both sides by the magnitude of the product of the magnitudes of A and B, okay? So since, we need to note that, since A, actually this is just the vector, yeah. Since A cannot be 0 and B cannot be 0, it follows that we can divide both sides by the product of A and B, okay? So if I divide this side, I'm left with just the cosine of theta, and 0 divided by anything is still 0. The cosine of theta equals 0. What angle is that true for? Take the inverse cos of both sides. Theta is 90 degrees. Okay, that shows that this works both ways. That's the if and only if situation. Therefore, two non-zero vectors, A and B, are orthogonal if and only if their dot product is 0. Now in part B, we're going to use what we know about orthogonal vectors and dot products, and we're going to find a vector that is orthogonal to a given vector. And this given vector is 3, 4, 5. Okay, it's in 3 space. We're looking for a perpendicular vector. Okay, so what is that other vector going to look like? Well, it's going to be in 3 space as well. So we're going to let x, y, z be orthogonal to 3, 4, 5. Okay, so this is the vector that we're looking for. If we can get a value for x, y, z, then we have found a vector orthogonal to 3, 4, 5. Now there are an infinite number of vectors in 3-dimensional space that are orthogonal to 3, 4, 5. We're just going to find one that satisfies it, okay? So there are an infinite number of vectors that are orthogonal. We're just going to take any vectors that are going to satisfy the equation. What is the equation? Well, for the dot product, x, y, z, dot 3, 4, 5 must equal 0. Okay? Now, I can pick any number I want for x and y, and I can find a z that makes it true. Okay? Why is that true? Well, because the dot product ends up being, just kind of off to the side, the dot product here is what? Well, it's 3x plus 4y plus 5z, and I want it to equal 0. So I can make this equal whatever, it makes no difference. I can pick any number to be x, any number to be y, and then I can solve for z that will make it true. Okay, and you could do that with any of the variables. You could choose a value for y, choose a value for z, and then find the value of x that makes this true. Does that make sense? So we'll start off really easy. We're going to let x equal 2, and we're going to let y equal 1. So now the dot product looks like this. If x is 2, then what I have is 3 times 2 plus 4y, which is 4 times 1, plus 5 times z equals 0. 6 plus 4 is 10, plus 5z equals 0. Subtract 10 from both sides. 5z equals negative 10. Divide both sides by 5. Z equals negative 2. Therefore, 2, 1, negative 2 is orthogonal to 3, 4, 5. And again, you could have picked any two values for x and y and find the z that makes it true, and you'd come out with a vector that is orthogonal. And you can check it back the other way. You could sub 2, 1, negative 2 into this dot product equation, sub it in for x, y, and z, and if it comes out with 0 on the right side, you know you did it properly, and you did indeed find a vector that is perpendicular to the given vector. Example 9, it's short and sweet. We're going to determine the resultant force in 3 space. So there's going to be 3 forces working on an object, and we're going to determine the total force. Okay, here's what we know. We've got a crane. It's going to lift a steel beam upward. The crane has a force of 5,000 newtons. At the same time, 2 workers are going to push the beam. They're going to use a 600 Newton force toward the west, and we're going to use a 650 Newton toward north. Okay, so let's see what this might look like. We've got this crane pushing it up, force of 5,000 newtons, and then we've got north, and again, I'm going to go positive directions here, except west, if you're kind of thinking of this flat plane. So if this is upward, then this XY plane is the flat plane, okay? And we can think of, if you're going around and you've got north, northeast, south, west. Okay, that's what that would look like if you can visualize it from the vantage point of Z, right? Looking down at this flat plane, northeast, southwest. All right, we're going 650 to the north. That's just a short guy in comparison to our crane. And then toward the west is negative in the x direction, okay? So that's 600 newtons. Negative. So here we have one that is 650 newtons. Here we have a negative in the east-west direction here. In the x axis, we have a negative 600. And the crane heading upward is positive 5,000. Okay, that's a visualization of what's happening here. 2 workers pushing on it perpendicular to one another, and a crane pulling it up. All right, we need to determine the magnitude of the resultant force that is acting on the beam. The 3 forces are all perpendicular to each other, okay? So we could separate this into 3 different vectors. We have a vertical vector, and then we have 2 horizontal vectors. We have horizontal west, and we have horizontal north, okay? The vertical vector would then be x, y, z. So we've got 0 in the x direction, 0 in the y direction, 5,000 in the z direction. This guy, the horizontal from the west, or toward the west, sorry, is on the x-axis. So he's going to be negative 600, comma, 0, comma, 0. And our vector heading north is on the y-axis. He's going to be 0, 650, 0. And all I need to do is put those together in the resultant vector, which is the sum of these vectors. So I've got the vector 0, 0, 5,000 plus the vector negative 600, 0, comma, 0 plus the vector 0, 650, 0. When I put those together, I get the resultant vector x, negative 600, y, 650, z, 5,000. Okay? That's the vector itself. That's the position that it would end up in our octant here. Now, what I need is the magnitude of the resultant force. So this is the direction that it's going in. And now the magnitude of it. Well, again, the magnitude is simply the square root of a squared plus b squared plus c squared. When you work that out, you get approximately 5,077.6 newtons. Okay? So there is a force acting on the beam of approximately 5,078 newtons in this direction. Okay? Done. Practice problems for 7.4 come from page 399, and you should be able to do questions 1 through 37. That's a lot. Pick and choose. It was a long lesson, so that'll take you a few days to get through.